In this clip, I'm going to provide an alternative proof of Taylor's theorem. Taylor's theorem, as you know, it says something about the quality of Taylor approximations of a function that is sufficiently differentiable, right? Suppose we have a function f defined on some interval, then if a is in that interval and Tn is the Taylor approximation, nth order Taylor approximation of that function in A, then we can look at the remainder term, and Taylor's theorem says something about the remainder term. So what does Taylor's theorem say? Well, if f is n plus 1 times differentiable, and if the derivatives are continuous on the interval, closed interval ax, and such that the n plus 1th derivatives exist for the open interval, then we can find for each x, we can find a psi of x in between a and x such that the remainder term can be expressed as such, right? So as the n plus 1th derivative in psi of x times x minus a to the power n plus 1 divided by n plus 1 factorial. So this one is what I'm going to prove, and I will use Cauchy's mean value theorem for that. Okay, what is Cauchy's mean value theorem? Well, it's built upon the mean value theorem that you know, but let's dive into Cauchy's formulation right away. We'll discuss the old formulation of the mean value theorem in the proof. So let f and g be two functions on a closed interval AB, and A is not equal to B, such that these are continuous. And suppose that these functions are differentiable on the open interval AB. Yeah, so, and moreover, suppose that g prime of x is unequal to 0 for all x in AB. Yeah, so the derivative of g does not vanish. The derivative of f may vanish, but not that one of g. Okay, so what does Cauchy now say? Well, there is a psi in AB such that if we look at the ratio of differences between FB and FA divided by GB minus GA, we can express it as the derivative in psi of F divided by the derivative of G in psi, right? So this is the Cauchy's kind of double mean value theorem, since it involves two functions instead of one. Okay, I will now provide a proof of this one. So what we're going to do is we're going to apply the mean value theorem first. We're going to apply the mean value theorem to G. Well, what is the mean value theorem? The mean value theorem says there must be a gamma inside AB such that the G of B minus the G of A divided by B minus A equals the G prime of gamma, right? So now realize that we assume that the derivative of G does not vanish. So this is always unequal to 0, right? Since B is not equal to A, we also know that GB is not equal to GA. So we could divide by GB minus GA, as this is a non-zero number. Okay, now we define a help function, and this help function is constructed like this. So it's just a linear combination of the functions f and g in a very specific way. So define a function phi, which is defined as fx plus some number p times the g of x, right? So p is some number in R. Okay, f is continuous, p is a constant, g is continuous, so phi is continuous on AB, right? And moreover, it's also, as a linear combination of two differentiable functions on the open interval AB, it is also differentiable on AB. Okay, but we can find we take a fixed value of p. We determine p such that we have the phi of b equals the phi of a. Well, how can we find such a thing? Well, just solve for the equation, right? So fa plus p times g of a equals the f of b plus the p times g of b. Well, it won't take you long to find the p, right? Just move all the terms to the left-hand side and concerning p, and all other terms to the right-hand side, and you will find that p is minus fb minus fb minus fa divided by gb minus g of a, right? Okay, now we are here in this world where we have defined a new function on AB such that this function in the endpoints, it is at the same level, right? So phi b equals the phi of A. Do you recall Rolle's theorem? So if you move from A to B, then there should be, in the middle of the interval, there should be a psi in AB with the property that phi prime of psi equals 0, right? So just try to figure out a graph of this function phi and see that there must be a point in AB, in between A and B, for which the derivative is 0. Yeah, this stems from the basic calculus course that you took in year 1. Okay, so we know that for this value, just calculate the derivative of phi in psi. The derivative of phi in psi equals f prime plus p times g prime, right? And this one should be equal to 0. Okay, from this it follows that p equals minus f prime psi divided by g prime psi. Yeah, but also we have a different formulation for this value p, right? So if we now put this one over equal to that one, then we're there, right? So we have fb minus fa divided by gb minus ga equals f prime psi divided by g prime psi. And this is the whole proof of Cauchy's mean value theorem. And we're going to apply it now. We're gonna use an additional theorem before we return to the proof of Taylor's theorem. We're going to prove the following, and you will notice that this theorem is much closer to the ultimate formulation of Taylor's theorem, right? So now suppose that we have an open interval, and A is contained in this interval. Suppose, moreover, that we have a function on this open interval, and this function is m plus 1 times differentiable on this I, right? Moreover, suppose that we have that fa equals f prime a, that all the function values and all the nth derivatives in a are 0, they vanish, right? Then what we can conclude, and we'll show this one, then for any x in this open set I except a, there is a psi of x in between a and x, such that now you'll see where the comparison with the Taylor's theorem comes from, that f of x equals f the m plus 1th derivative in psi x divided by m plus 1 factorial times x minus a to the power m plus 1. Yes, and this one is what we're going to show. And this one we will later apply directly to the remainder term. So what does a proof look like? We're going to use Cauchy's mean value theorem. So first assume that a is smaller than x. Well, if x is smaller than a, the proof is analogous. So it's almost the same, right? So you should try it yourself. Now, take g of x equal to x minus a to the power n plus 1. This means that g has a lot of derivatives, right? So it's infinitely differentiable since it's just a polynomial, right? Okay, also notice that if we look at the derivative of this function, that on the open interval ax, the derivative of this function is unequal to 0, right? It is 0 only for the value x equals a. Okay, now let's go. So Cauchy's mean value theorem now states that inside this interval ax, there should be an x1 contained in the open interval such that the difference, such that fx divided by g of x, or fx, we know that fa equals 0, right? So we can write it as fx minus fa, and g of x is non-zero, but the g of a, if we plug in a in the description of g, we find a minus a, so that one is 0, so we get g of x minus g of a, right? So here we have the differences of the endpoints of the interval ax, and Cauchy's mean value theorem says that there is an x1 in ax such that uh, this ratio of the differences of the function values over this interval equals the derivative of f in x1 divided by the derivative of g in x1. And we can write this down since x1, the derivative in x1 is unequal to 0. Okay, now we're going to apply the same reasoning basically to the interval ax1, but we're going to apply it to two functions f prime x1 and g prime x1, right? So we're going to write, I'll do it a little bit faster, f prime x1 and g prime x1. We can write a little bit differently because this is just f prime x1 minus f prime a. Remember that the derivatives of f in a are 0. And also, if we take the first order derivative of g is still 0, right? So assume that n is larger than 1, then also this derivative vanishes. So Cauchy's mean value theorem now says that this ratio of difference of function values can be written as the ratio of the second order derivatives in some point x2 in ax1. Yeah, like so, right? Okay, but then we can continue and now apply Cauchy's mean value theorem to the functions defined by f double prime and g double prime, right? So we just continue by doing the same thing, the same reasoning, right? So we use that fa is f prime a equals the nth order derivative of a equals 0, and the same holds for g, right? So now continue, and we find ultimately we find an xn plus 1 in axn such that the nth order derivative of fxn divided by the nth order derivative in xn equals, yeah, we're still gonna write it differently, right? So the nth order derivative of f is still 0. We can write it as fn xn. We're gonna write it as the difference between two values. And here below we're gonna write it as a difference of these two values, right? So notice that g is defined as x minus a to the power n plus 1, so that the nth order derivative in a is still 0, right? So now we're going to apply Cauchy's mean value theorem, and we're going to show that there should be an xn plus 1 in axn such that this one equals the n plus 1th derivative in an xn plus 1 divided by the n plus 1th derivative of g in xn plus 1. Okay, but now return to this function, right? So g is x minus a to the power n plus 1. So imagine what happens if we calculate the derivative of this function n plus 1 times. Then the only thing that is remaining is n plus 1 factorial, right? So what we get is that now we find the following, is that we started with fx divided by g of x, and we found x1 in ax, and etc until the n plus 1th derivative xn plus 1 divided by the n plus 1th derivative in xn plus 1, and they are equal, right? So we had equality all over, right? So we started with fx divided by g of x equal to f prime x1 divided by g prime x1 equal to f double prime x2 g double prime x2, etc etc, so that in the end we find fx divided by g of x equal to these two n plus 1th derivatives, right? Okay, from this one we get that fx equals, we multiply the left and the right by g of x, right? So we get the constant, the n plus 1th derivative in xn plus 1 divided by the n plus 1th derivative in xn plus 1 times g of x. Yeah, but we also mentioned that the n plus 1th derivative of g is no more than n plus 1 factorial, right? So basically this is equal to some element, let's say xi of x. Xi of x can be defined as xn plus 1 divided by n plus 1 factorial times g of x, and g of x, right? So that's n factorial, but g of x is x minus a to the power n plus 1, right? So this completes again the following theorem. So finally we are ready for the proof of Taylor's theorem, right? So we're going to use the last theorem. We're going to apply it to Rn of x, right? So we have fx minus Tn of x, right? So we know that this function Rn is n plus 1 times differentiable, right? Since T of n is just a polynomial, and this is infinitely many times differentiable, and f is assumed to be n plus 1 times differentiable, right? So we know that Rn is n plus 1 times differentiable, so that we also have, because of the tangency between f, between the graphs of f and n to the order n, we know that a lot of derivatives of this function r in a are vanishing, right? So we have the kth derivative, where k is chosen between 1 and n. The kth derivative equals the kth derivative of f minus the kth derivative of the nth order Taylor approximation. Yeah, but the nth order Taylor approximation is exactly the polynomial which is tangent to the function, to the graph of the function to degree n. Okay, so now we have this function Rn, which is n times differentiable, and a lot of derivatives vanish, right? So the last theorem then says that there should be an x, xi x, in between a and x, such that the f of x, well, what is the f of x here? Well, in this theorem, this is the Rn of x equals the Rn of xi x, where we take the n plus 1th derivative of this function divided by n plus 1 factorial times x minus a to the power n plus 1. Yeah, but now have a look. What is this term here, right? So we have Rn and the n plus 1th derivative of Rn. But here is a polynomial of degree n. So if we take the n plus 1th derivative of this polynomial, we get a 0. So only thing that we end up with is the n plus 1th derivative of f. And this is exactly what we need. Since now we have Rn, the n plus 1th derivative is just the same as the n plus 1th derivative of f minus the n plus 1th derivative of t. And then we just plug in this result over here above to get the f n plus 1th derivative of psi of x divided by n plus 1 factorial. Here I should add a factorial, n plus 1 factorial times x minus a to the power n plus 1. So this completes the proof of Taylor's theorem through two other help theorems, two lemmas. That's it.